Great. Hi, everyone. Thanks for joining our masterclass on graph-powered machine learning. I hope you're enjoying NoCon 2020 so far. My name is Thomas Deely. I'm co-founder of the Knowledge Graph Conference. We're partnering with Connected Data London on this year's event and very excited to do it. Before I hand over to Jörg, I will mention that we also have a Slack channel which is open throughout the event for you to post questions and continue the discussion even after today's session right through the end of the conference. So with that, I will hand over to Jörg, who's the head of machine learning and engineering at ArangoDB for his masterclass on graph-powered machine learning.
Thanks so much for the introduction. I will kill my camera to save some bandwidth, which hopefully is not going to overload the platform. But yeah, thanks for the introduction and welcome to our masterclass on graph-powered machine learning. Let's actually jump right in. Most important piece here, lower left corner, I'll give you like one more second to get that link if I get rid of this annoying bar here. This will actually get you to the slides and to all the exercises as they are linked from the slides. I'll repeat that on a later slide, but this would be a good time to just copy over this link and get access to all the material here. Otherwise, what will you learn in this session, in this class? So the TLDR is basically, if we are utilizing relationships within that data, we can actually do much more than we would just do machine learning on the data itself. And I try to group that into three different areas. And the first one is kind of graph analytics, answer questions from graph data itself. The second one, and this is where we're going to spend the focus of this masterclass on, is graph embeddings and graph neural networks, basically learning graph and graph structure. And the last part, for which we most likely won't have time, is on graph-based machine learning metadata. So this is more an ops topic, but basically even here, graphs can be super useful to keep provenance of data and to keep track of but challenge is we have 2 hours for this. So this is why I try to put some focus area here. And so here's the kind of overall agenda. And here in the middle part, on the orange part, this is where we'll spend most of our time. This is where we want to have the focus. But actually, the workshop is also up to you. So feel free to suggest what you want to focus on here. I'm Jörg, I'm the head of engineering and machine learning at ArangoDB. Prior to that, basically my entire career, I've been switching back and forth between building database systems, starting like doing my PhD on distributed database systems. Then I built a lot of data and machine learning infrastructure, based machine learning infrastructure. And now I'm kind of happy that I can both combine the large-scale distributed system ArangoDB. So as mentioned, this workshop is actually for you, so feel free to put any of the expectations, questions, feedback you have into the chat. But I really prefer in-person workshops because the interaction really helps you to get content across and also to ask questions to see where people might need more time, where people might want to go faster. So this is all a bit more challenging in a virtual environment. So let's work together on that and just put things in the chat if you have any questions here. Question for the link to the other masterclass workshop. It's being backed by a link is down here. So feel free to just go there, but we'll also have links to all the different in the slides itself when we. Okay, to kind of get started, and I feel always this is one of the most interesting aspects about the workshop, it's just the breadth of problems we can actually answer from a graph perspective when we look into graphs. So from the TLDR, from those three areas we are having, so what kind of problems can we actually solve here? So in graph analytics, there's a vast majority from like community detection, identifying like common subcommunities in graphs, over to recommendation engines, identifying central nodes in a graph or in a community, pathfinding. Those features are being detected from a graph analytics algorithm, and then they might actually be used as some other kind of machine learning workflow. So often here in this first part, we also do feature engineering for a larger machine learning problem. The second graph, the second part is focused on, like, as mentioned, like learning graph structure itself or graphs itself. And here we often deal with like node or link classification. Imagine we have a link and we have a large graph of like consumers, and we try to identify the most. Imagine you're either LinkedIn, Facebook, or some other social network, and you try to a link between two nodes in your user graph, and you try to figure out and predict which other connections might make sense in this graph, so they can send you an email and try to grow your network. Last is also classification of entire graphs. So basically take an entire graph, turn that into a feature, and then leverage that for classification. And this is often used in like drug discovery, or also like other graph classification problems where I try to view the graph as an entire entity and then move forward. Focused on the operation side of machine learning. We can focus on problems such as data provenance, audit trails, privacy concerns, and other things coming up. So let's dive in and briefly talk about what graphs are. I assume everyone knows. That's why I'll go rather quickly, but feel free to stop me or tell me to go faster if needed. So yeah, graph-powered machine learning. So I think one of the key aspects when we talk about graph is that relations or connections are actually a key property of your data. So if you have to classify, do I store my data in a relational database? Do I store my data in a graph model, graph database? Relationships are very important, and for example, also your queries are a lot about those different relationships, then probably a graph data model is the best fit for you. Graph data models that might have a graph database which is built on top of a columnar database, on top of a relational database, but often that actually comes at a performance cost. So graphs, we often talk about directed or undirected graphs. And here an example is, for example, Facebook or Twitter. In Facebook, a friend relationship is actually mutual. So if I'm a friend with you, for example, then you're also my friend. So it's an undirected graph because there's just an edge in between. Whereas with Twitter, we might follow someone, but that doesn't imply that this person is following us back as well. So it's a directed graph. We can have weighted graphs, which means on the edge, so how closely are they connected, and they might contain cycles or might be acyclic if they don't. And yeah, sparse and dense is kind of we have a range of queries, but typical graph queries often end up with traversals. We want to find out how certain nodes are connected. So how can I get from A to B? What is the weight or cost from getting from A to B? Is satisfying a certain criteria. And this is, for example, often the case in fraud detection, where you want to look at a node and read patterns throughout a graph. There are a number of graph databases out there. Probably the most prominent one is Neo4j. There's in the online world, data models, Tiger Graph, and as mentioned, I actually if we look at how we can store graphs from the database perspective, and here in the knowledge graph camp, we are probably very familiar with the RDF or triple store side, where we store graphs or represent graphs basically as triples with subject, predicate, and objects. The nodes don't actually have any internal structure, and we're used to querying that with Sparkle and are probably using some ontologies and logic for inference on top of those knowledge graphs. The typical graph databases here on the prior slide, with the exception of more follow like a property graph model, where each node can have certain properties. And this kind of collapses the graph. And you also have a different set of languages, such as Tinkerpop, Gremlin, Cypher, or AQL. I would say both have advantages and disadvantages. But they can also be, I don't think those camps are actually talk, and we'll put that into a blog post soon as well. Property graph and RDF, friends of fools. And I strongly believe that actually both sides can learn and interact with each other. Overlap in the middle. And so, for example, this notion that ontologies and logics, that they are mostly used on RDF triple stores, is actually not true anymore, as a lot of property graph models and databases are implementing that as well and supporting that as well. I have here an optional lab for Sparkle. So if you never interacted with Sparkle, I will just open that to show you how this works, but I won't go through the entire lab because but the lab structure is kind of set up like this. We leverage Colab from Google. So Jupyter notebooks. And here, this is being based in a Jupyter notebook. And Jupyter notebooks are super great tools to actually share a combination of documentation and executable code. Yes, I know. Yes.
Could I pause you, please? Your audio is still dropping out regularly, and I think it's making it difficult for people to follow. If you would like to try, we could
then just give me 1 second. I'll switch over to a different source.
Okay, no worries. If not, I could do the slides for you off my machine.
1 second, so I'll drop out for 1 second while I switch.
Welcome back, Jörg.
All right, so I'm now on a different audio internet connection.
So we press on and see how it goes.
Yeah, I'm sorry for the connection. Didn't jumping back to the notebook here. So this is the nice thing about those Colab notebooks. You can basically just run the code here. And so this should give you an easy example if you never worked with any Sparkle or any RDF data store to just get a feel for that. So just run through the node. Go through and get a short understanding of that. Okay, jumping back to our presentation here. Go back to presentation mode. There's a second notebook. This is more focused on the property graph side. So also, if you never worked on the property graph side, it nicely also shows the difference, how you would model things differently between RDF and property graphs. Let's get started with machine learning. And so if you're new to machine learning, a really great source to get started here is for me Fast AI, especially as they don't focus just on deep neural networks. I feel in machine learning right now there's a trend to focus on deep neural networks, and we'll also focus in this talk a little bit about those. But there's actually a large number of a simple regression, which can actually help you to solve a lot of your problems before. So in general, why is machine learning taking off right now? And so, or differently asked, why are we actually turning those people sitting in front of a screen into superheroes who can do like this really cool stuff, aka our data scientists, who all of us want to hire right now? And this is mostly due to the combination of three factors. First of all, we have large amounts of data available right now. And secondly, we also have the compute resources to deal with them, including on Google. They have those TPUs for machine learning tasks. Last but not least, we also have a really big improvements in machine learning algorithms and machine learning research, which helps also leverage these compute resources efficiently to process the large amounts of data we are seeing nowadays. And with that, we can do for drug discovery. There are also newer papers which actually leverage deep graph networks for that. There are deep Bach, which is like a composing neural network, and just listening to that, if you to which are the kind of like by the AI, and with that, it's really hard to distinguish both of them. To answer the question, which was on the chat here. So here, for anyone who hasn't didn't get the link yet to the slides, I just repasted that in the chat. Should otherwise also be at the very top of the slide deck. This is kind of this new trend. And we do a lot of the feature processing in traditional machine learning, where the pipeline works as follow. We get like some data input, data scientist sitting there.
Jörg, can I interrupt you again? You are still dropping out for considerable bits of time. Would you like me to play the slides from here if you stop screen sharing and I share, and you just say next when you want me to move forward?
Then I'll stop sharing.
Okay, bear with me 1 second.
Interestingly, I don't see any package drop in the background. At least if I'm pinging Google.
Could you just where you wish me to get to?
Yeah, slide 26 here.
But I cannot see numbers, so just when I get
there. You just got there.
Okay, just say next whenever you want it changed.
Okay. Interesting challenges in virtual times. So yes, in deep learning, kind of the promise is that we can actually replace this manual process by just adding more data and more compute. It's actually just done by a lot of data and a lot of compute. It's not really the case in reality. So any feature extraction into a lot more benefit, and is a vital part of this pipeline. Next slide, please. So how the process actually looks like, and the most important part, one-time process. So we have two different sides. We got the training side. We get a lot of labeled input data. We run we train our deep neural network. The inference part is when we can actually leverage that to get output or real classification of some live data. So this is basically where we can extract value from our trained model. Next slide, please. The important thing to keep in mind is how often we are doing things here. So the training part is something where we actually run a lot of times through this deep neural network, and we also do that rather often. So we don't just train a single network, we actually train a with different hyperparameters. And then we try to identify the best model in the end. And here, the computational resources are also much less because we are basically just doing one pass through the entire model and not a lot of back and forward pass. So the expensive part typically is the training aspect here. Next slide. Okay, this finally brings us, and now we can put a combination of both to graph useful in a lot of different areas. So for example, from fraud detection, you might have heard of the Panama Papers trying to identify tax fraud. It can be used in enterprise hierarchies, for example, for permission management. It can be used in the Internet of Things. So for example, a bill of material for large airplanes is also certain analytics on top. Representation learning, how can we how can we classify certain nodes in a graph? These are all things we can cover in graph-powered machine learning. Next slide. One example is, for example, the fraud detection example. So I included this example to showcase how you can actually model something as a graph. So we have our information. This is a bank collection. Then a bank can have branches. So this already is a graph. Branch can have different customers. Customer can have accounts between different accounts. And you can already see this actually forms a rather large and dynamic graph as you have more and more transactions coming in. And so with that, you then want to do analytics on this graph to identify where, for example, fraudulent transactions. So if you consider money laundering, you're often looking for kind of cycles in this graph where you're trying to get a lot of money moving around in a specific circle through this network, but eventually all reuniting in one or multiple accounts. Next slide. The other big about, which is why I'm skipping over some of that material, was machine learning. And here we're seeing also just this is really like a growing field where more and more companies are moving from this, more and more users in general are moving from this simple something into production. That. Next slide. Of course, the question should be like, what makes graphs so special? What is the difference between representing something in more a tabular form? So for example, here, if you look like form with a lot of links and self-references, or we can actually represent it as a graph. Was the visualization actually process that in parallel just by looking at how dense in a more tabular form. We first of all have to one row at a time. And secondly, we then also have to kind of build up this mental picture in our head. Also, just from like a computational perspective, often we can address certain problems much easier in a graph setting than we could in. And this is simply because if we have to represent a graph in a tabular form, often we end up with a lot of cells. This is usually rather inefficient from a processing perspective, whereas in graph, it's that we can actually rather quickly follow graphs out, whereas otherwise we end up with a lot of joins, and joins is kind of the hard problem in relational databases because they can become really expensive. Next slide. Feature engineering. As mentioned, one of these things which graph analytics, feature engineering. And feature engineering refers to the task of into a normal machine learning framework such as tensor tool you're using, but those tools, they mostly work with relational input. They basically can convert graphs into vectors later in this presentation. But this is like an often a process where we have some graph data. For example, a feature could just be you have a LinkedIn network, and the feature you want to extract is like how on Twitter, how.
Jörg, I'm so sorry, I'm going to have to speak to you again.
Like
the audio is no better, and people are beginning to have to leave. Someone mentioned in the chat, is it possible it could be a hardware issue? And is it at your end, as you have no ping problems, is there a reboot anywhere that might help, or is there some action we could just take for 5 minutes that might improve this?
Yeah.
So I'm trying to use another mic here.
Okay, thank you.
And yeah, I'm super sorry for that. From jumping back to the feature engineering part, and let me know if this is any better. So here we actually take our data, we extract features as, for example, the with a tabular form, which we can input into something else, such as TensorFlow, MXNet, or our favorite machine learning framework. Next slide. Next slide. Rob?
Everyone, I can see that Jörg is just disconnected, which I'm sure is just him rebooting his machine or changing some hardware. So hopefully he will be back soon. Welcome back, Jörg.
So I now just rebooted everything, and I'm really sorry for that, but I have no clue where this is coming from. Okay, can you hear me?
Yes, we can.
Okay, let's hope for the best. I'm sorry for that. Can you switch to the next slide? Okay, so let's dive into graph analytics then. And as mentioned, next slide, please. This is can be classified as like what do we want to do on certain graphs, and probably the algorithms we look at often first when we start computer science is search. So find a particular node or edge, and examples for that are, for example, breadth first or depth first search. This kind of problem is path finding. How can I get from A to B? And so, for example, traveling salesman, or like any Google Maps application where I want to go from A to B is an example here. It gets more interesting if we look at centrality or community detection. So centrality is pretty much the question, what are important nodes? So for example, our influencers. If you were Instagram, Facebook, and you try to identify the kind of people where you're going to reach out to most people, you want to look for those central nodes which are very well connected. Similarly with community detection, if you want to identify certain subgroups in your entire graph, community detection is a very good approach here. Next slide. So community detection, as the typical algorithms for that are, for example, triangle count, or identifying strongly connected components. Or another really interesting one, as it's iterative, is label propagation, and we'll also see them in one of the in the lab coming up shortly. Next slide. Really interesting example here is for graph algorithms is collaborative filtering. And I usually like that because it highlights what you can actually do, or how many things can be driven by such graph algorithms. And probably all of you have seen an example. So for example, on Amazon, customers who bought this also bought a particular other item. And if we now want to go in how we can actually build that, it would be, next slide, please. Rob, can you switch to the next slide? Thanks. It would be basically, how can we build a movie recommendation system? So in Corona times, we always want to know what should we watch next, and so how can we build a recommendation system for what to watch tonight? And there's a lot of data available. So for example, IMDb, they have a lot of ratings out there, and this can be modeled as a very simple graph is rating a certain movie. Next slide, please. And now we can actually, using that graph, we can look at which movies I like. And so if we have to express it as a question in collaborative filtering, it's can be formulated as such: find highly rated movies by people who also like movies I rated highly. So basically, I want to find people who are similar to me, and then I want to find movies which they have rated and which I haven't seen before. So if we have to go through that, we can do the following. We go in and we first find movies which I personally, as a user, I rated with 5 stars. And this is basically a traverse in this direction where I, as a user, I find like over the rating connections, all the movies I rated highly. Next, I want to find users which also rated those movies highly. So from the set of movies here on the right, I want to go back that edge, that rating edge, and identify users who also rated the same movies very highly. And then last but not least, now I have a set of users. I want to go back in the other direction and identify other movies which were highly rated by those users. So this is an example how we can express a simple task as a recommendation as a graph analytics problem. Next slide. Furthermore, we have other graph algorithms such as pathfinding and search. So as mentioned earlier, search is around how can I identify a certain node within that graph. And so I want to see, is there a node with X, value X, for example? Is there a certain product available? When I'm building a large airplane, are we leveraging a certain part which might have been recalled from the FAA? And so I have to go through that entire graph, and there are several strategies depending on my kind of problem. So I can either go breadth first, so first kind of spanning out to all other nodes, or I can go depth first. Furthermore, pathfinding, this is about how can I get from A to B. And here, for example, shortest path or k-shortest path are very simple and famous and also very versatile algorithms to deal with that. Furthermore, often I'm interested in minimum spanning trees. So how can I find like a minimum subset of my overall graph, which is forming a tree? And last but not least, and we'll see that where that comes in handy, often I'm interested in just random walks across a certain graph. So random walks, it basically means at each node, I'm taking a random edge and follow that. And this is very useful if we want to get a representative view of, for example, the graph, or if later we are actually building representations and trying to put that in a feature vector. Next slide, please. Is the audio better like this?
Yes, it is.
Okay. So can you just click on that link? Down there, the Colab link. Rob, could you click on that link?
I have. Sorry, it opens it in a different tab, which is not the one being shared.
Okay.
Apologies. I need to stop sharing and share a different tab if you want to see that. That's important.
Okay. If the audience has already done that, it's basically just an implementation if you want to run through the collaborative filtering example. Then for now, let's just move to the next slide and discuss more about graph algorithms here. So other important problems in the graph algorithms range is about centrality. And centrality, it identifies nodes which are very vital to a graph. And the notion of what might be vital to a certain graph is dependent on, your problem. So this is why we have a large number of different measures for what means centrality in a graph. So probably the easiest one is degree centrality. And that simply measures how many in and outgoing connections does a certain node have in a graph. And so in that sense here on the right, this blue node actually has the most number of in and outgoing connections. So this would be the node with the highest degree centrality. The next measure, this would be the closeness centrality. And this actually comes to which is the node which is on average close to all other nodes. So basically you compute the distance to all other nodes, and then you identify the average distance to all other nodes. The interesting thing, especially and that betweenness centrality, this basically refers to how often is a node on the shortest path between some other nodes. Rob, are you still sharing? So how often is a node on the shortest path between other nodes? Or asked differently, if you would remove a certain node from a graph, in how many different subgroups, how easily would the graph deter in terms of connections there? And this is, for example, also very important to identify central nodes if you have like a flow problem. So if you need to disperse information in an, for example, internet or other network stack, this is a very important node which helps you to identify the nodes which you might want to replicate, or at least you want to monitor separately because they're kind of important. If they fail, you might have a problem. The last one is PageRank, and PageRank stands for kind of like a notion of transitive influence. So, so far, the other measures we've looked up here are only concerned with just from the structure of the graph itself, which was helped by Google. It's kind of like this founding algorithm of Google. It also has like a certain measure of influence on each of the nodes. Next slide, please. And this actually works by an important, more important, or if we look at how Google actually viewed that, if you were yourself, if you were a website, how highly should I rank you? So how influential do I believe you are? And I believe you're more influential if a lot of websites are linking you, which are by itself important. And so the kind of way to become important is twofold. You can either be linked to from a lot of random sites, or you can be linked to from like a very few, very highly influential sites or very important sites. And this will increase your importance yourself. Next slide. The other question, how we can rank or view the PageRank problem, is actually like a random surfer. He's just surfing a web page. He's going to click a random link and will follow that. How likely will he end up on your site? So this is like, we can just simulate that over and over. And there's the notion where we, for example, have random walks coming in handy. So as mentioned, random walks, it's a useful tool for a lot of different problems on graphs. And here, random walks are actually helpful to, for example, to identify PageRank over a long time. But luckily, there are also other algorithms. And this is basically done by always distributing my rank to the neighboring nodes. So I basically tell all the neighboring nodes I'm linked to, hey, this is my importance value, and thereby you can also iteratively compute the PageRank of each individual node. Next slide, please. As such kind of iterative problems are very common on graphs, Google actually developed an open source framework or an open source algorithm. There are multiple implementations of that called Pregel. So Pregel is a system for large-scale graph processing, meaning it allows us to actually process graphs over a large number of different nodes, aka large number of graphs. And another notion of such kind of algorithms is bulk synchronous processing, because they all follow a certain number of super steps. And so what Pregel basically does, in each of those super steps you can see here, each node will communicate with all its direct neighbors, so it can send a message to all the neighbors. The next step is each node will process all the incoming messages and then send another update. So it's this very simple formula of like we receive them and then we send a message to all our neighbors. How can we actually do something or solve a problem with that? Next slide, please. And so this is a very simple problem where within a graph, we simply want to find the highest value. This was just the easiest to draw, but the same process actually works for all other kind of Pregel algorithms as well. So it's active. People send an update to all its as finds a maximum value. This is simply the value of ourselves, or the highest value we are currently have seen. So the 6 is going to send a 6 to all its outgoing connections. 3 is going to send a 3, and vice versa, and vice versa. Then at the next super step, each node will process the incoming messages it has received. So if we, for example, take a node, it's the upper node on the left, originally the node number 3, it has received a message number 6. So it will compare that with its own value. Okay, 6 is higher, so we'll update our own value. And this actually also means we're still active and we have to send a message in the next message iteration. If we look at the original node number 6, node number 6 has received 2 updates, 3 and 2. They are both lower than 6, so nothing changes, and we also don't have to send updates. So this is kind of important to minimize the traffic. We don't send this number 6 again. And so only the nodes which have changed are sending another update. So this is the left upper and the right lower node. They are sending another update. And so in the next iteration, the only node for which that actually matters is the right upper corner, which is sending, which is changing its value to the 6 as well. It now has indirectly received from the node in the lower right corner. And once this is done, there are no more updates in the graph, and Pregel kind of converges. So the convergence in such Pregel algorithms, often it's either done when there are no changes anymore. As in real-life systems, this is very unlikely to happen. Often there's this threshold where you say, if we are only changing our value by 0.01, then we consider ourselves halted and don't change anymore. Okay, this is Pregel, and this is very useful for a large number of different problems, and this is also why it's implemented in a lot of different frameworks such as Spark, ArangoDB. We also have it implemented Neo4j, and so this is a very common pattern. Next slide. Is also one of the tools implementing. And so NetworkX, it's a very, very nice tool. I would call it kind of the Swiss Army knife of graph processing. It allows you to load and store graphs, analyze network structures, build network models, design new network algorithms, and also visualize it. So often I wouldn't necessarily leverage NetworkX for real large-scale analytics, but I would use it to do exploratory analysis of smaller graphs fitting into the memory of like a single machine. Next slide, please. And yeah, this is something where we would have again a lab. Rob, should I actually try to regain sharing after I restart it?
Yes, good idea.
Okay. 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 This seems to work. And just let me know once the connection goes bad again. So again, this is our NetworkX notebook. We need to do the usual magic. loading all the Python libraries, cloning that Git repo. This should just take a few seconds. And now we can actually start playing with our first graph. Feel free to play along on the side. As mentioned, I feel this is a very useful tool for whoever wants to leverage graph or play with graphs and do analytics on graphs. So typical name, and you see that often also if you look at code involving network X. So network X usually is referred to as NX, and then I can add edges between nodes. So the nodes here are actually added implicitly. So if I'm adding an edge from 1 to 2, and then from 2 to 3, this will implicitly create the nodes 1 to 3. I can also explicitly add nodes, for example, here by adding like a particular node called spam. Once I have that, I have a large number of different algorithms, and those are the algorithms we actually discussed prior as well. So for example, I can just print the connected components of a certain graph. And the connected components here, we got 2. So this is a connected component we can get from one node over to the other, and we have another connected component here. And I can also show the degree of all nodes in my cluster in my graph. So here, node number 1 has degree 2, as we have 2 edges going out. 2 has 1, 3 has 1, and spam actually has a 0. Furthermore, we also add node attributes and connections. So it's kind of a labeled property graph. You go back. And this allows us to draw like more complex graphs. And this also, if you later want to try something with, for example, pathfinding or shortest pathfinding, you can simply add weighted edges here, for example, from Boston to Berlin in between. It also comes with a nice number from different graphs. So often if you're trying to identify edge cases or just want to try out a certain algorithms, there are certain random graph generators. And so, I mean, the easiest one is just give me a complete graph. A complete graph means each node is connected with all the other nodes. We can simply do that. And if you just look at the documentation, it's also linked up here. You can get a lot of the if you're dealing with graph algorithm on a random graph. So far, we only dealt with in undirected graphs. So you can see that, as we said up here, nx.graph. This gives us an undirected graph. But we can also create other graphs. So for example, the kind of trivial one is the graph, where then we actually have, this is if we look at, for example, would later print the degree. Feel free to do that. Just copy over the degree code from here, g.degree. You would also see different in and out degrees here. Okay, how can we leverage network X to solve like a real-like problem? We can build like our rating example, like our movie rating example here. And so something just to show you what's happening here in the beginning, we're actually cloning the repo. So the repo backing this, it includes a CSV file with the different ratings. And if we just do a head, so this is also nice about Jupyter notebooks if you never worked with them. If you put like an exclamation mark here, this is simply as like a shell command supported in there. So you can also, if I just want to add like a new one here, you can also just do like an ls, for example, to show what's in the directory, and thereby also just leverage normal Unix shell commands to see what's going on in your environment. And here we just simply leverage edge, and here we can see this is the ratings data we are having. We have a user ID rating a certain item, in our case a movie, then we have a rating, value 3, and our timestamp here. And so with that, we can actually build our network X graph. And the nice part is this will take a while, as this file is actually really large. But with that, we can load our graph, and now we can actually build the same application with the movie recommendation we have done before. Feel free to put in the chat. So I originally planned to actually do that now and then show you like some of the cool stuff. For example, adding different colors for different node types. As you might notice here, like both movies and users are actually displayed in the same color. But there's Network X makes it really easy to add different colors here. We can easily find the most rated movie, highest average rating, and as mentioned, also implements the algorithm we have seen there before. In terms of time, I would suggest to first go through the presentation and just leave that up to you. Those notebooks, they just stay there. It's running on Google infrastructure, so you can just access them at any time. Feel free to put in the chat whether you would like to have some time to basically just play with that right now, or whether we should move on in the slides. And I'll also be later available in the Slack, obviously, so you can always just ping me if you have further questions, also to make up for the data delays here. Okay, let's move on. Okay, next in the agenda are graph embeddings. And just a short detour, so because this is also one of the very famous graphs which you can also just generate in Network X on the fly. It's one of those in there. And this is the karate club example. So there was like a local karate club, and that karate club, the president and the head coach, they actually got in a fight, and then they split that club into two. And the nice part is that there was some study before, and so it was very noticeable who interacted with which other members before. And so this is kind of like one of those common graph problems, is like which of those different members is going to join which subpart of the club. So the kind of like splitting nodes is node number 34, which I believe is the president, and number 1 is kind of the head coach. And so kind of a graph classification problem always used, a classic one is who is joining which part of the club. And this is basically trying to predict certain connections in that graph, which you also have in, for example, networks such as Facebook, where people are trying to predict the either strengths in this case, or also missing connections in a graph example of previous interactions. And for that, we have to talk about something called graph embeddings. And this is the case as machine learning in general mostly works on vectors. So what we want to have a function, and a typical one is called node to vec, which takes an entire graph and it's outputting us some kind of multi-dimensional, potentially multi-dimensional vector. And so if we talk about embeddings here, we can talk about different embeddings. We can first talk about vertex embeddings focused on the vertices, and also entire graph embeddings if we actually want to compare different graphs. So and the question is, do I turn a representation of a single vertex embedding? Do I want like 10 representation of this one node here, so vertex embedding, or do I want an embedding of the entire graph so I can compare different graphs? And what would we like to have if we have such, if we create such embeddings? We actually want that similar nodes are creating a similar embedding. So what do we mean with similar nodes? So if we look at a graph, there's different kinds of similarity. So first of all, here, if we look at those two nodes, and this is the homophily equivalence, they are directly connected. So if we create a vector representation, we would actually expect them to have like similar vectors. Similarly, structural functions. So if we compare the node U here in the middle to node here S6, they seem to serve similar functions in the entire graph. And so we also want to have a similar representation for that. And this makes this problem of how do we turn a node representation into a vector pretty challenging. And to understand that, let's just have a look at a similar problem, because this is actually where most of the research for that is coming from. And this is about how can we turn a word into text, or a text into a vector. The easiest, if we start out, would be one-hot encoding. So if we have a sentence, "Have a great day," we simply take the first word, map that to 1000. If we have the next word, we map it to 01000. Good is 001, and so on and so on. Of course, this leads to very large vectors, and they don't contain much information, as everything but one position in that vector is set to 0. And it's also still very hard to extend that if you want to add more to the dictionary. Second problem with that is that we want the similarity between two words. We want that represented. So here, as I just received random vectors, the distance between them is actually all going to be the same. So I don't have any notion of expressing something similar, that two words actually have similar meaning. So for example, good and great, we would expect, as they have similar meanings, that they actually have similar vector. And here, maybe just as a reminder, what we typically consider as similar with vectors is the cosine similarity in between. So roughly speaking, how big is the vector, how big is the angle in between those two vectors? And so word2vec was one of those approaches which helped us to do the same for text. And so in text, we actually do that by having a lot of example text, which allows us to classify and come up with a model for that. So the assumption here is words appearing in the same context, that they actually should also be close by in terms of representation. And so with that, we actually generate a kind of dummy skipgram network. So how does it look like? Pairs from all our source text. So this is like a brute force approach. We go through all the text, and here we're looking at, for example, here two distance to each side. So here with Z, we generate the training example Z, quick, brown, and here are two training examples. Next, as said, we go 2 in each direction. Look at the neighborhood, 2 neighborhood. Quick, we generate the training examples quick Z, quick brown, quick fox, so all the words in the neighborhood, and so on and so on. So next, with those training examples, we actually generate one hidden layer. So here's our input with the different words. We have one hidden layer, and then we have our output layer, our output word we would like to predict. So here with Z, we would like to predict quick, and brown with high certainty. What I'm interested in is this hidden layer here in the middle. Because if we look at that, we can actually treat it as a word-to-vector lookup table. So we train this network, and this sets some values here in our middle network. And now if we look at this middle layer in a matrix representation, so if you're actually looking at deep neural networks, in the end, this ends up like a large number of matrices. And so how that would look like. Here we got like 10,000 words as input, so that would be a 10,000 in this direction. And we decided to have 300 neurons, so kind of the complexity of our hidden layer. We get 300 neurons here, so this is a factor we can control ourselves. And that actually leads to a word vector lookup table, as we can treat that as word to 300 feature vector lookup. So by that, if we actually only interested in this middle layer as a lookup table, we end up as by a representation for our words. And so if we want to look up the word vector for ants and the similarity with cars, we can take our lookup for the vector ants, multiply that with our output vector cars, just add a softmax to normalize that, and then we have the probability that a random word is going to be nearby, that the word car is going to be nearby ants. And so this is kind of the idea of a skipgram model. And in Word2Vec, that we train this dummy network here. We just take the hidden layer as a representation. And as we train that with those training examples generated, we actually end up with a closeness or similarity measure, which helps us to condense these features down to 300, to a vector of 300 for the features. Okay, words can be easily sampled from a text, right? So if we look at text, this is simply linear, so it's really easy to define the neighborhood of a word in a text. How can we do something similar for nodes in a graph? And this is what Node2Vec is concerned about. And so how can we sample nodes from a graph? And again, we do that by doing random walks. So the first model to actually represent something as, to represent a graph as an embedding, so basically as a vector we looked at, was just to do a random walk. So we just said we're doing a 3 random walk from this node. So this would be like T, 1, 2, 3, and this would be our training pair. And with enough, we would generate those examples. What is kind of the downside of that? It doesn't really both the homophily equivalence. I mean, I can stay rather close if something is close by, so this is partially represented, but the structural equivalence is not really well captured in that, as I'm just doing a random walk in any direction. And this is why Node2Vec then actually introduced sampled random walk. So it was a guided random walk. We don't take a step randomly, but we take that on some guiding principles, which is determined by some hyperparameters. And this looks as follows. Imagine we have just moved from T to the middle node V here. And now we want to figure out what is the next step to take. So this has been the last step we have taken. And now as we have a guided random walk, we actually want to know what is the next step. So the kind of random one would be here, just takes that one. And this is controlled. The interesting notion of this is that this is connected with this node. And so here, this is this middle case here is basically if there is a notion between and the distance between T and X is actually 1. So we're staying within the same subcomponent of our graph. This is case 1. We can control via this hyperparameter / we actually control that through the other hyperparameters, as typically this is set to 1. So this is case 1. Second case, easy case, is what happens if we just directly go back. So in this case, dtx is 0 because we actually end up on the same node, so distance from T to T is 0. This can be useful if we want to stay within our same subgraph. So if we're really only interested in the close neighborhood, we might actually want to set the probability of going back rather high, because this means we'll just explore the subgraph here. The other notion, what we can do or what we might be interested in is exploring further. So basically, we don't want to stay in the same subgraph, but we want to have a very high probability of exploring far, far away parts of our graph, of our network. So in that case, this is the the Q parameter here. This is basically the probability of moving from V to either X2 or X3. Note again, they are not connected to the same subgraph here. They are not the same node. So this is basically reaching out to further nodes somewhere further down in that path. And so I would refer to that as kind of the probability of exploring the entire graph. So with those parameters, you can actually guide how you want to generate those training examples. And then it's the same with the skipgram again. So note to that, we're doing the sampling with random walks with our parameters here. Then with that, we can train our skipgram model, and then we can actually compute our different embeddings here. And this leads to another workshop. I'll just show the exercise, but won't go through the entire detail. Just basically give you an idea so you can run it afterwards yourself. Again, we simply start by doing the same in network X. So here there's a node-to-vec implementation. And what I would recommend you to do is actually just play with those different parameters here. So to maybe just go through, dimensions refers to like how big should the intermediate, the hidden layer be you want to train. The walk lengths, how many steps do you want to take? How many walks do you want to take? And just how many walks do you want to have in parallel? And then also you can set, if you look at the documentation, which is usually something nice working in here. Okay, let me see. Colab used to have really nice code completion. Maybe I have to run that first. So let me just do that. For the code completion. So this allows you to actually play with that and then also look for more similar nodes. So depending on how you tune those different parameters, you'll get pretty different results. The next is actually a very cool example based on here a Kaggle data set. And this allows you to predict and generate embeddings for soccer teams. So just from FIFA, we have nodes which are players, team names, and positions. And in the end, this actually allows you to see that different positions are similar to each other. People in or players within the same team are similar to each other. And so basically see how those graph embeddings play out and how the similarity is. So I just find that like a very visual example. The other thing which is a bit annoying about it, but also serves like real-term use cases is you have to do a lot of pre-processing here. It's explained here, but this is also what unfortunately often ends up with real-life data sets. You have to do a lot of pre-processing. Okay. So this is about node embeddings. Maybe just to recap, it's basically a method of representing either nodes, which can then compare them to see which nodes are similar to each other, or also put them
Jörg, your audio is completely gone. Sorry, everybody. Jörg has lost connectivity. Hopefully she'll be back in a second.
Okay, I start to doubt that this is me being kicked out here.
Yes, you just disappeared. So whether live webinar has threw you out, I do not know. It's just very sudden. You're back with us though, so hopefully we can continue.
Yeah. Start to, as I said, like my pings are also very stable here. Sorry for that again. So as mentioned, next we'll look into how to actually predict something about graphs themselves. And this is the area of graph neural networks we'll dive into. And the first is about graph convolutional networks, where we are looking into most likely topology in graphs. And also later spatial and spectral graph convolutional networks. So convolutional networks, if you're a bit familiar with what's happening in like other networks, is we try to do a convolution over usually where it's usually coming from. So we like a four grid here, and we are moving that over the entire picture and try then to either condense it or generate other features. This, of course, is much harder if we're looking at a full at a normal graph, because in a picture with pixels, pictures are very regular. They have neighbors next to each other, and so from that we can actually just go over here. So we're sliding kind of like our window over that. If we talk about graphs, this unfortunately is not possible because we don't have this regular topology. So here, how would we slide our window across that graph? Each node has a different number of neighbors, and there's also no like really easy number of sequences we could follow throughout this network. And this is actually driven a lot by Thomas Kipf. I also later have some more links in the Keep on Reading section. But the idea is basically, how can we have something similar we have for convolution in normal images for graph structures. And this basically follows a similar approach we have already seen in Pregel with kind of message passing between nodes. So imagine each of the nodes can pass a feature vector to its neighbors, and then we just compute kind of the new weight accordingly, and we again do that very iteratively. So a similar idea we had in Pregel, we are passing on a message to our neighbors and then updating our own weight. But let's actually see how that works from the mathematics itself. And so this is a notebook I would actually run now because I find it's very useful. So again, just loading all the different libraries, cloning that, and then let's build kind of like a toy graph convolutional network. The cool thing about graph convolutional networks is that they surprisingly work even though we might not have trained them before. So there are a number of research papers about them because they actually can move forward without being fully trained, just leveraging the network structure. So here we generate a very simple network. And just in case you haven't seen that, this is another way of representing graphs. You can actually
Sorry, folks. Seems like the same problem again. Bear with us.
It's a platform dropping me out.
The platform appears, you appear to mute for quite a while and then you're disconnected. I cannot see any reason from this end, I'm afraid. I'm sorry you're having such a terrible time.
No, I'm sorry for the audience. It's not me. I mean, the audience. I know my slides. I'm sorry for the audience. Okay. So I basically just said, hey, we can generate our graph here. And what we are doing now is we generate that from the fly, a graph convolutional network from the fly to just understand the mathematics being involved here. So here we have our graph. And the next thing is we actually just want like some feature representation. So something describing each node. And this would be what we want to learn about that graph. So it might be the color of a certain node, a certain price, or any feature you can imagine on those nodes. And just for simplicity, right now we'll just leverage the different node IDs here. So 1 and -1 for each of the nodes. So it's very, very, very simple matrix. So the hidden layer inside a neural network, and there we come in a graph convolutional network, can actually be seen as just a function of the structure we have up here and the structure, our feature vector. So in the end, the simplest function we can have is just a times x. So we just take our matrix and multiply that by our feature vector. What does it do to our neighbors? So our feature vector will be multiplied by the adjacency matrix and hence be moved over to our neighbors. So how does it look like? So actually now this will give us for each of the nodes the sum of all its direct neighbors. So here, node 1 is probably the most interesting. It receives the updates from a lot of surrounding nodes. So this is why we have here 5 - 5. This only receives one update with 1 - 1, and here we have 2 - 2. What we are still missing here is that we are kind of losing our own value, right? So we only kind of get the features from our direct neighbors, but we are missing out on our own feature. So it's very easy to fix. we simply fix the adjacency matrix to include ourselves. So with that, if we do that, it's basically, we can also just print that. This is a nice thing about this. We can just do stuff on the fly. And let's actually print a head. Yeah. And run that once more. So here, this is the same adjacency matrix we had before, but we're simply adding on the diagonal 1, so each node is connected to itself. So we'll send ourselves that feature vector as well. And now if we look at that, we see this increasing a bit over here because we actually send our own value to ourselves here as well. Okay, very, very simple. What is still a problem here? That higher nodes with high degree of connections, they'll simply end up accumulating and ending up with higher and higher values. So for example, see here, this is a highly connected node in our graph, so it will just accumulate a lot of values. So we kind of want to normalize that. We can simply do that by the number of the degree. So how often is our node connected? And this is basically here, our matrix here, our degree matrix. So we do that both for the original matrix. So 1 has 1 outgoing connection to node 0 has 1 connection, 1 degree. Node 1 has 2, 2, and 1. If we include the self loops as well, 2, 3, 3, 2. Very simple. If we do that here, we end up with the degree, and we can do the same computations as before, basically passing the information over to the neighboring nodes. So this is very, very simple. And as for now, we simply computed this step like x times or a hat 2 by now, as we moved that several times x, is very static, and there are no parameters we could learn because we're simply taking the weights, and if we wanted to learn something for this network overall, it wouldn't be very helpful. Of course, there are no parameters we could learn. This is why in graph convolutional networks, you then add a certain number of parameters, we are adding the weights which can later be trained. Last thing, and this is if you're a bit familiar with neural networks, you want to have a linear activation function. So even though here we have some weights here, so basically our multiplication here would be so adjacency matrix times features times weights. We could train those weights, but in the end, it wouldn't really help because it's just still a linear problem. So all we can express with that is a linear problem. As we want to have a deep convolutional network, we need to make it nonlinear. So we're actually adding a nonlinear function, and the easiest is actually the Rayleigh function here. And with that, we can simply do like a hat times x and just wrap that entire thing in Rayleigh. And with that, we have kind of built like our first one-layer deep convolutional network, or it's very shallow because it just has like one node. But in the end, I feel this was at least for me very helpful to understand also the connection between deep neural networks, because this is the same principle, right? We are ending up with matrix multiplication around that, and the connection to the message passing we talked about in Pregel before. And this is why I actually felt it was super helpful for me, at least, to include this as well. About that comment in the chat, I will record this later on my own laptop, just going through. And Rob, I hope you have a way to kind of like distribute that and share that.
Yes, we will do that.
Yeah. And as I said, I'm sorry, I'm having a ping running here in the background to just Google, and this has so far like 0 drop packages. Okay. So back to the Karate Club example. So I said, like, the challenge we we want to have here is we want to classify who is ending up in which part of the club, right? So are we either going to join here our president or our trainer in nodes 1 or 34? Cool thing is Network X, as this is such a famous example, already has the karate club in there, and we can simply draw that. It's not as nice as this drawing, but in the end, this is the same graph. Oh, this should just be a text node. Sorry. I'll change that later. So from our graph here, we actually extract the adjacency matrix, so to NumPy matrix. And then as before, we are following the same steps. We're adding the self loops. So again, this is just the identity matrix. Imagine on the diagonal, we are adding those different nodes. We are creating the degree matrix. Recall the degree matrix, we leverage that to normalize it by the number of degrees, because otherwise just highly connected nodes that would just accumulate more and more values over time. And for now, let's actually just introduce the weights again randomly. So here, just random weights, done. And then for readability, we simply wrap like our GCN layer. So the same thing we built on top, multiplying those different things into a function. This is just for readability later on. This basically generates one layer. And now with that, we can already create our first neural network, or our 2-layer GCN network. And this is basically here in the beginning. This is the node representation is just identity matrix, so one hot encoding. And then we push that through our network. And with that, we can already see that certain nodes, so for example, node 0 is very likely going to end up in our example here, in kind of the first graph, which makes sense as this is like the trainer, and the last is also. So basically, if we run that over and over, and this is something I would leave to an exercise, if you add more and more layers, what will happen, you'll see it will start to converge to certain certain groups. And this is a nice part about those GCNs, that just based on the graph structure we have here, so who is connected with whom, this will actually help us to train this network. And in that next notebook, what we would do is basically there are some outputs where we can see who actually ended up in which part of the club. And this is then how we can train this network and predict even for members where we don't have much information about in which part of the club they would end up in. So, yeah. Okay. Switching back to the slides. And the next tool, I mean, right now we built all of that from scratch. But the tool which makes it a lot easier is a deep graph library. So a deep graph library is originally brought up by Amazon together with, I believe, Singapore University, and they make this entire thing a whole lot simpler. So this is basically just about doing the same thing over, but with a decent library. I'm not going to run all of that, but pretty much you will see the same code here, a very similar structure, but you can just generate that embedding and other things much simpler, and you don't have to code everything. And here then at the end also follows the training steps. So even here in the beginning, what we do is we just label 2 nodes, and these are the instructor and president nodes, and they get a different label. And then we can just, as in a normal neural network, use our optimizer and train our neural network. And the cool thing is that actually you will see that even without much training. I mean, this is not much information you're putting in. You're simply labeling the instructor and precedent node. You already get a pretty good output within like a few training runs. So Deep Graph Library, it also includes a lot of tools for entire like graph classification. So graph classification, for example, is something a cycle graph, a star graph, and you can train a graph convolutional network to actually decide that. Okay. Okay, GraphSage. The problem we solved so far was about, we were dealing with fixed graphs, right? I mean, the embeddings we generated and this structure, if we train something, what will happen if that graph changes? And so this is one problem with those graph convolutional networks we looked at so far, is that they won't be able to deal with unknown or changing graphs. So I would say like changing graphs is probably the more common problem, because simply those graphs won't be static over time. You'll add edges in between. So we actually need an embedding function which can generalize to previously unseen nodes. Recall that even our node to vec only works with fixed graph structure and doesn't generalize to new graphs, simply because the matrices and they are basically fixed. And so this is a kind of the goal what GraphSage tries to fix. So they try to come up with a more general label. And the second aspect they're really doing a nice job on is that they can also work with very large graphs. So if you look at the previous tools, they won't really scale to very large graphs because these computations don't scale that well. You basically are communicating with all neighbors. And so one advantage of this GraphSage is that, first of all, if I had to highlight what's in the title, is that inductive representation learning, meaning it will work with unknown graphs, and it also works with really large graphs. So how do we do that? So in our input graph, we have a target node. And from the target node, we try to come up with a generic representation. So for that, we consider the neighborhoods around that. And so here, this means we're kind of considering like this a black box here, and then just consider like all the inputs to a black box. And there we are again at a structure which can then, as we are not dealing with a particular node, but we are generating the features from the neighborhood. So here, this will generate a black box of kind of feature, and we are leveraging that and not the direct node representation. From that, we can actually leverage the inductive part of that. In the nodes down here, and sorry, I'm just trying to rush a bit, but I feel there's a very interesting bonus lab here available, which goes into more details here, how that works. And I'll go through that in the recording I will create, because I feel it's actually rather interesting and important. But basically, the two things is, first of all, we can aggregate over the neighbors, kind of this black box we saw earlier. And secondly, this also helps us to scale around larger graphs, because I don't have to consider the entire graph when doing this computation, but I only have to consider the local neighborhood. So I can actually scale this computation to rather large graphs. As said, I'll run through this example because I think it helps to have some more explanation to what's here when I'm doing the recording. But feel free, there's the bonus lab is already mentioned here in the slides down here. And key part is the inductive and large graphs. So this is something which helps us to work with changing and unknown graphs, and also larger graphs than before. similar graph attention networks, which basically generalize that even like one step further. So in that neighborhood, they actually allow not just generate a fixed representation, but they actually allow to learn what information, what attention should be passed on to that. So graph attention networks, they allow us to have something, for example, to identify like very important nodes in a graph. If we look at graph stage, all the nodes are pretty much like similarly important, and we just graph them randomly in our neighborhood. And here in graph attention networks, we can actually identify core central nodes which should have a higher importance compared to other nodes. So if we look at how those things rank in complexity, if we look at embeddings or what we can get out of that, we have we have deep walk on the left side. So this is very simple to recall. Deep walk is basically we're doing a random walk over the graph, and from that random walk, we then go in and generate the embeddings, train our skip RAM, so this dummy network, and this gives us an embedding and vector representation of our network. Node2Vec is improving over deep walk by having guided random walks. So we're introducing those parameters, so we're not just randomly jumping from one node to the other. So, but we have a guided random walk where we go in from and decide, do we want to go back? Do we want to stay in the same subcomponent? Or do we really want to explore far away parts in this entire graph? Graph convolutional networks, they allow us to do that similar feature passing, and thereby do actually exchange information of that graph. So here, Deep Walk and Node2Vec, they are not concerned with any additional information, any labels we might have on those nodes, but graph convolutional networks, we can actually pass on those features. GraphSage, again, allows us to get to represent an embedding by sampling the neighborhood. So this black box is basically a sampled version of our local neighborhood, allowing us to also work for previously unseen nodes and also for very large graphs, as we don't have to consider the entire picture, as this is a sampling step. And graph attention, then on top of that, helps us to identify central, more important nodes, and kind of keeps that attention what should be important in our feature vectors in the embedding here. So with that, I just want to point back to different implementations which have implemented that. So if you want to keep on playing with those kind of tools, I would actually recommend the Deep Graph Library. We have seen that in the Karate Club example earlier. And it's a very versatile tool. It works across different backends. Probably the easiest is still the PyTorch backend. Also like my favorite, but feel free to choose any of the other backends available there. So with that, and I wanted to reserve the last 5 minutes for listening. If you don't have any questions, I'll jump back to one of the examples earlier. But I wanted to give some more pointers where to go from here. So first of all, if you're more interested in the first part of this talk, there's the Graph Algorithms book from O'Reilly with many practical examples. I don't find the implementation examples in Spark and Neo4j too helpful, but overall I find the structure of different graph analytics algorithms rather helpful. Then from Manning, there is under development, so it's not, the book isn't done yet, but you can get a preview version, the graph-powered machine learning book. And otherwise, there are a number of really cool web resources. So highly recommended is the Stanford course on machine learning with graphs. You can get all the slides from previous iterations. The next iteration will be like in winter 21, but you can get all the content and just browse through those lectures. And this is like a really deep into graph-based machine learning. So highly recommended. Others is Thomas Kiff. I think he's now a research fellow with Google, but he was one of those early people driving the graph structure representation, developing early graph convolutional networks. So this is also a very good way to get started. And then also just look, he has some really good tutorials out, and if you go down here, he usually also has Jupyter notebooks for all his publications. There's a really nice repository for seeing the different graph representation learnings. So typically what happens here, this person, he is discussing one paper, and then has like a Jupyter notebook and a blog post next to that. So here we cover like deep walk, graph convolutional networks, graph sage, and then spectral neural networks and graph attention networks. Okay, and last but not least, again, this is also under development, but you can free download the pre-publication book, PDF. And also highly recommended is the book on graph representation learning to get started. Or also like go very deep into those topics. Okay, with that, I would open it up for questions you might have. And secondly, I would also ask you to tell me what else you would like to focus in the recording. I don't know, Rob, I think it's okay with the recording if I go over 2 hours. As you can see in the slide deck, there are actually other multiple sections here, and I blanked out a lot of slides because originally this was developed for a 3-day PhD workshop in Denmark. And I'm happy, and also feel free to hit me up on Twitter and others, but what else I should include in that recording. Can also be after this talk, but feel free to tell me which parts you would like to focus on. I'll just run through all the content, so it's most likely will end up being a bit longer than the original 2 hours intended here. But as I said, feel free to hit me with any questions or any content you would like to have covered in that recording. And again, sorry for the audio trouble. I'm not sure. I'm doing Zoom meetings all day long, and I didn't have any trouble today.
Thank you, Jörg. I've opened up to discussion, so anybody can verbally ask a question. You don't have to type them anymore if anybody has a question. I think there is a question in chat, a comment.
Yeah. As said, this is a topic which is also very dear to me, as it kind of combines all my passions from databases over machine learning, and then also building like machine learning infrastructure, which kind of is the last part, where it's, again, very terrific how versatile graphs are to different problems.
Ah, you have a question from Daria in chat. Should be appearing. Can you see that?
Yeah. So, what is the greatest struggle graph implementation still has to resolve? So, I think there are multiple issues. So, first of all, from mapping things down there, I think we can leverage a lot by bridging the gaps between the RDF kind of group of people. So, kind of the strong description logics based, or even like, I don't know, seen some first order logic based knowledge graph implementations with the ease of a relational with a property graph example. So kind of just how can both worlds work together in making complex inference easily accessible. Second challenge I'm still seeing quite a bit is just a sheer scale. So a lot of the graph databases are simply not scaling to a larger number of nodes. I won't go into detail as I might be biased there, which ones do. But basically, how can you implement such things at scale? And then it depends a little bit on your problem. So as mentioned, I'm a strong opponent for starting with very easy and explainable algorithms. So start first with graph analytics, and just first when you really understand your graph data, go into this deep convolutional networks, generate those embeddings, because then it gets a bit harder to explain what's going on. So scale, explainability, and kind of moving together the different subgroups, developing similar systems but in different directions.
I think we are now out of time. Thomas has had to go for another session, and I believe this room will then be used as well. So thank you very much indeed. Well done in such difficult circumstances.
Yeah, I'm looking forward to next year having such thing in person. Thanks a lot, everyone, for sticking around despite the challenges.
Thank you.